Students, can you please respond quickly? My screen is visible to your end.
Yes, sir.
Yeah, thank you. Actually, in our class, we have started with the wave equation concept. In that, we have started with the uniform plane wave and some of the properties we have seen, and followed by that some matrices we have seen, and also in wave propagation in different medias we have seen. Okay, so after that, I have give brief on Maxwell equation. I have not proved this thing. Maybe in next class with this wave equation, I will tell about this Maxwell equation. In today's lecture, we going for pointing vector. So, what is the pointing vector? The pointing vector is nothing but the power flow. Okay, so usually it will mm, predicts the power flow of the medium, given medium. So then, what is the purpose of finding this pointing vector? So whenever you can see this slide, I have mentioned that that waves is propagating in the free space in a medium. Okay, in a medium. So then there you can find one in red color and another one in blue color. There is red color is a electric field, blue color is a magnetic field. Both are transverse with each other, that is perpendicular to each other. So this is literally called as the polarization. Okay, this is literally called as the polarization. So when E and H is there, okay, when E and H is there, if we making E vector and the H vector, then we will get the power P. So this entire thing is called as the pointing vector. Okay, this entire thing is called as the pointing vector. So this thing only we going to study. The entire procedure and the step what we going to follow is called as the pointing theorem. So by using the pointing theorem, we're going to analyze what all the matrices will come in that equation, and finding maybe whatever radiation it is, it has the both electric and the magnetic property. Okay, so let me go with the what is meant by the pointing theorem. When an electromagnetic wave propagates through space from their source to distance receiving point, there is a transfer of energy from the source to the receiver. There exists a simple and direct relationship between the rate of this energy transfer and the amplitude of electric and magnetic field intensity of electromagnetic wave. It is a theorem. The theorem is nothing but what it is one hypothesis relates to that particular vector. Actually, simply vector we have denoted at top like this. Okay, so P is equal to E cross H. So this is nothing but literally a polarization. So what is polarization you have studied? It is nothing but the orientation of electric and magnetic field. Students, if any one of them waiting outside, please let me know so that I will give admit option. Okay, in between, um, you can. So let me go with the what is meant by the pointing vector. Okay, so the pointing vector, I have given the expression. I will give the statement. The vector product. Okay, the vector product of electric field intensity of electric field intensity and the magnetic field intensity. The electric field intensity is denoted by the symbol E. You already know. Like magnetic field intensity also denoted by the symbol H. Okay, at any point. Okay, at any point means in the free space only. At any point is a measure of the rate of energy flow. The rate of energy flow per unit area at that point. So once again, I repeat the statement. The vector product of electric field intensity and the magnetic field intensity at any point is a measure of rate of energy flow per unit area at that point. So this is what we have given. So P is equal to E cross H. P is equal to E cross H. Okay. So even then, this pointing vector concept is a derivative. Okay. But this time you have to know the what is the main thing. Okay, main thing that only very important. But when this concept is one of the very important concept, usually it will be asked in your gate exams also. Okay, so for this concept, I will take full derivation. Okay, and this may be really useful whenever it will be applied for that is upgraded subjects like antennas and then microwave, etc., etc. So you can see the first equation. It looks like the how that is the direction of the flow P is perpendicular to E and H. So this is the basic concept from the vector calculus. So I can write the statement. Why means it these statements are very important for your MCQ. Okay, for the flow P is perpendicular to E and H. So maybe in a MCQ it may be asked like this means either the direction they may ask or else perpendicular. I have given a symbol. You have to write in a word. Okay, single word. Okay. So either the direction you should know or else a perpendicular you should. Okay. So this is one of the important statement, and also this is your definition for your pointing vector. And then please remember the pointing vector, sorry, theorem statement also that I will give. When an electromagnetic wave propagates through space from their source to distant receiving point, there is a transfer of energy from the source to the receiver. That means what? Now I am talking to you. I am the source point. You are receiving my signal. So those who are having the good bandwidth of the signal, you will receive with some good delay. Maybe some those who are in remote area, you will get my signal very late. But the thing, everyone will receive my signal. Okay. So in terms of the electronics, that is in circuits, you have studied about the maximum power transfer theorem. So my signal can be term it as a power also. Okay, my signal can be term it as a power also. So if the potential and the current is there, okay. So in a circuits you have studied like this, like P is equal to V into I. That is simply remember VIP. Okay, VIP. Okay, VI equal to P. Okay, so power is equal to V into I in the electronic circuit level. Okay, so in the EMF, the same power you are relating in terms of the electric and magnetic field. So in terms of circuit, how can I tell? The maximum power is transferring from the source point to the end point. The source point to the end point. So when how can we calculate the electric field equation and as well as magnetic field equation? There is some procedure is there. Let me go with the procedure with the proof. Okay. So before that, I want to show what is in reality. You can see this simulated zip file. Is it visible, students? My zip file is visible to your end. Is it visible?
Yes, sir.
Can, yeah, yeah. You can see that the waves is propagating from the dipole antenna. So in a dipole antenna, there is a two polarity, positive and negative polarity is there. In one end, we are getting an electric field, on other end, we are getting a magnetic field. So you can see the movement of the electron is going towards that dipole. Okay, so how it's moving with respect to the load resistance. I have given only one portion. Please imagine it is your transmitter part. Okay, so this signal should be received at the receiver part. So the best example is your FM radio. So in FM radio, what you will do? So in each of your mobile phone, you have your FM radio applications. So once you get into that application, it has the different station signal. So when you tune that value, so what is that value? Some values are displaying like 93.5, 102 point something or 100, like that different stations are there. So that is nothing but your frequency. So the frequency and the wavelength can be related like this: lambda is equal to C by F. It is one of the basic formula you are studying from your school level onwards. Okay. By using that only, the communication devices are explored. And that is your base equation. Okay, base equation. In that, many communication needs are hidden. Okay, so if we are in our hand, many smart devices or intelligent devices are there, electronic intelligent devices are there. So everything is based on the simple concept like Kirchhoff's law or Ohm's law or this type of that is what a pointing vector theorem, etc., etc. So so now in this thing, we're going to explore what is the what is meant by your pointing vector. Let me go ahead with this theorem proof. Um, yeah. So the energy flow equation can be obtained from the Maxwell equation. Okay, so the energy flow equation can be obtained from Maxwell's equation. So in Maxwell's four equations I have shown, by using that only we're going to do it. So by using the first Maxwell's equation, I am simply putting ME. ME stands for the Maxwell's equation, the first Maxwell's equation. So if you remember, you can tell, or otherwise I will write it. Del cross H is equal to J plus J plus dou D by dou T. Like this we have studied. Okay, so del cross H is equal to J plus dou D by dou T. So we know that D is nothing but what? It is a dielectric flux density. Okay, it is nothing but dielectric flux density. So we know the value for D is equal to epsilon into capital E. So once you substitute over here, so epsilon is the constant, please take it out, dou E by dou T. So del cross H, J plus epsilon dou E by dou T. I'm going to express this equation with respect to the current density J. So then how can I write this equation? That is J is equal to del cross H. If I take this term this side minus epsilon into dou E by dou T. Okay, dou E by dou T. So now I am further what simplifying this equation. So I'm going to multiply with the electric field. So multiply, simply put the cross symbol, multiply electric field on both sides. On both sides. It will be nothing but the power per unit volume. So that is E dot J, which is equal to E dot into del cross H, the first term, minus epsilon into E into dou E by dou T. Okay, dou E by dou T. So now we are going to apply here some vector identity form. Okay, now we are going to apply some vector identity form. Then we are going to apply here. Okay, so what is the vector identity form is that let me go with the notation of E and H. Vector identity. Okay, in vector identity, del dot E cross H. Okay, del cross E cross H can be written like this. H dot del cross E minus E dot del cross H. Correct. So this is one of the vector identity. So if we have denoted like A cross B, so instead of A cross B, I have denoted like E cross H. So then in before equation, you can see that we want this term. If you see, we want this term. So you want to express like this. So I am taking this side. I am going to take this equation. This part to this side, and this to this side. So then it becomes like this: E dot del cross H is equal to H dot del cross E minus del dot E cross H. Okay, so then in above equation, please see, can have E dot J. So instead of E dot del cross H, okay, so I'm going to replace this term and the remaining term I will be writing. Okay, so that is E dot J, which is equal to H dot del cross E minus del dot E cross H minus epsilon E dou E by dou T. Okay, but what is your second Maxwell's equation? Okay, what is your second uh, what is your second Maxwell equation? I'm simply putting ME. Okay, so it is del cross E is equal to minus mu into dou H by dou T. So you can see del cross E is there in your previous step. I'm going to replace that part. So then E dot J can be revised like this. E dot J is equal to, so minus mu into H, dou H by dou T minus minus um, epsilon E dou E by dou T minus del dot E cross H. So actually I have suppled the Okay, actually I have shuffled the term. Okay, so we're going to apply. Actually, you can see there is a two partial derivative term is there. Okay, two partial derivative term is there. So how I am going to relate? You can see. So you can see h dot dou h by dou t, e dot dou e by dou t. Okay. So how I am going to relate? You can just see. Okay. So it can be written like this: h dot dou h by dou t is nothing but I will tell that is half dou by dou t h square. So if you just differentiate this term, okay, just to differentiate this term, how you will get 2 into h, okay, 2 into h, correct? 2 into h into h. That is 2 get cancelled, okay, 2 get cancelled, and h is outside is there, and one function will become here, correct? So I have written this h into dou h by dou t like this. Similarly, he dot dou e by dou t also written like this. This half dou by dou t e square. Okay, e square. So now you substitute in the above equation. So then in above equation, you will get like this: E dot j is equal to minus mu by uh, 2 dou by dou t h square minus epsilon by 2 dou by dou t e square. It is a second order function minus del dot e cross h. Okay, del cross e cross h. So please see, this is for one wire, a small point. So if I am considering this is one big conducting medium, for this small point I will got E dot J. But I want what is the total current flowing this conductor. Then what I have to do for this entire volume I want. Then I have to integrate. So then only I can know what is the total Pointing vector for this conducting element. Okay, so then I have to integrate on over to this, integrate on both sides. So why I'm integrating? To get the entire volume. Okay, to get the entire volume. So that is E dot J into dV. This is a volume integral. Equal to, you can see that in both the equation, dou by dou t is a common term. Okay, both the terms, dou by dou t is a common term. So I can write like this: minus dou by dou t whole volume integral of mu by 2 h square plus epsilon by 2 e square into dv. Okay, I will write it here itself inside. Okay, I will write it again so that it will be precisely come inside to this border. Yeah, once you integrate like this, I will draw like here itself. E dot j into dv, it is a volume integral, which is equal to minus dou by dou t of a volume integral of mu by 2 h square plus epsilon e square by 2 into dv minus the volume integral of del dot e cross h into dv. Okay. So now you see this expression, it will be look like a divergence. Okay, it will be look like a divergence. So if I apply here, okay, if I apply here, this a del dot to this thing. This can be, okay, this can be replaced like this. A volume integral when you apply the divergence theorem. I'm simply writing THEO theorem. So it becomes a surface integral of E cross H into ds when you apply for this. Okay, when you apply for this. So then the above expression will be comes like this. Then the above expression will be comes like this. So integral, that is volume integral of E dot J into dV is equal to minus dou by dou T of volume integral of mu by 2 square plus epsilon by 2 E square to dV minus the surface integral. You can see these two are volume integral. Okay, these two are volume integral, where this one is your surface integral of ds. So then I'm going to give the unit for this, the power dissipation, and the power dissipation, the power dissipated per unit volume. So why I'm telling unit volume means it is multiplied with a J. Okay, it is nothing but a current density is nothing but E dot J. Sometimes they will ask the power dissipated per unit volume is dash. Then you can write E dot J alone. Okay, E dot J alone. Whenever you writing the denotation, the same letter, it's in the capital, it's in the without any space. Okay, without any space. The unit for this is nothing but watts per meter cube. Okay, watts per meter cube. So how watts per meter cube? Can see the electric field. Okay, the electric field unit is nothing but what? Volt per meter. Okay, and what is meant by J? Current per unit area. Okay, current per unit area. The I is nothing but a current, and A is the area. So, what is the unit for the current? Ampere. And what is the unit for the ampere? Sorry, area, meter square. So, A per meter square. So, if you put as this thing means you will get the volt. This is a volt. Volt into ampere is nothing but a watt. Okay, so this one is the meter cube. So, what only we got the watt per this thing. So the physical interpretation of this expression for the law of conservation as follows. Actually, this entire thing is called as the law of conservation. Okay, I will give you the statement. The interpretation, physical interpretation of this expression from the law of conservation of energy. So, what is the law of conservation of energy? Energy neither be created nor be destroyed. Okay, so you can see the terms. Okay, so you can I will put it in the different color. Okay, so this thing is nothing but the first term is called as the rate of energy dissipated in a volume. So this is your second term. So this is called as the rate at which the stored energy in volume is decreasing. Why? So minus sign is there. Similarly, you can see another thing. It is a E cross H rate at which the energy is entering the volume from outside. Okay, I will turn this thing into the next slide so that it will be really useful. The first term is nothing but the rate of energy dissipated in volume. Dissipated in volume means the entire wire dissipation in a volume. It is in the entire wire, which is equal to, that is your second term, rate at which, okay, rate at which the stored energy in volume V is decreasing. The third term is that the rate at which the energy is entering the volume from outside, entering the volume from outside. Okay, so this is what uh, pointing theorem. Okay, pointing theorem means this thing you should know. That is pointing theorem comprises of all three. If it is a pointing vector, it is nothing but P is equal to E. So why we doing this thing? To find out the power flow per unit. With the help of this pointing vector only, we are determining the pointing theorem. Okay. I hope this concept is clear to you. If you have any doubts or clarification, you can stay back and you can ask question. Now I will call up the name for the attendance.